Hey everyone, and welcomes to this explainer. Look, we live in an era of incredibly shiny, high level abstractions, right? We've got these beautiful cloud dashboards and serverless architectures that honestly feel a bit like magic. And it is so easy to get completely mesmerized by that interface. But if you actually sit down with experienced enterprise cloud architects, the folks who are out there building and rescuing these massive distributed systems, they're going to tell you a completely different story. For them, the ultimate differentiator isn't knowing the layout of the latest dashboard, it's having a deep fundamental understanding of the Linux kernel. Because here's the hard truth. Linux remains the absolute backbone of cloud-native platforms. There's this running joke in our industry that the cloud is really just someone else's computer. But if we're being accurate, the cloud is really just someone else's Linux machine. Every major modern cloud platform is built right on top of it. From Kubernetes clusters down to individual containers, all the way through your automation and observability tools, Linux is the actual engine powering the agility, the scalability, and the reliability we demand today. It is not just some legacy operating system. It is the active, beating heart of modern infrastructure.
So here is our roadmap for today. 1. The cloud-native illusion. 2. Anatomy of the migration failure. 3. Unmasking Kubernetes and containers. 4. SRE and DevSecOps reality. 5. Linux networking and scalability. And finally, 6. Mastering the foundation.
All right, let's jump straight into Section 1, the cloud-native illusion. This is a trap I see platform engineering teams fall into all the time. Cloud-managed services, think AWS, GCP, Azure, they provide these incredibly user-friendly abstracted interfaces. You click a button, boom, a database spins up. You write a single line of code, and a fleet of web servers scales globally. It's awesome, but it creates this false detachment. It creates an illusion that you no longer need to care about the operating system. But the gritty reality, underneath those polished API calls, every major public cloud is orchestrating massive, massive fleets of Linux servers. And when things break at scale, I promise you that dashboard won't save you. Which brings us to Section 2, Anatomy of a Migration Failure, or what happens when you ignore that underlying OS. Picture this. A massive enterprise is executing a 10,000-node lift-and-shift hybrid cloud migration. Everything looked absolutely perfect on paper. The cloud provider's dashboard showing all green lights. CPU usage looked fine, memory was totally within bounds. Yet, down in the trenches, the application was timing out, services were inexplicably dropping, and latency was just through the roof. This is exactly what we call the 10,000-node blind spot. Relying purely on those high-level cloud dashboards completely masked the critical, underlying system issues that were literally tearing the architecture apart. So what was actually happening? Well, first, they hit exhausted file descriptors. The application was trying to open way too many connections, and the Linux kernel basically just said, nope, no more. The shiny dashboard completely missed that. Then they slammed into DNS resolution limits right at the kernel networking stack, which meant microservices couldn't even find each other. That led to massive routing bottlenecks. It just proves what veteran architects already know. You absolutely cannot troubleshoot a distributed system at massive scale without a fundamental understanding of Linux ports, services, and foundational routing. You need visibility into system performance that literally only kernel-level metrics can provide. Let's move on to Section 3, Unmasking Kubernetes and Containers. Let's apply those gritty lessons to the tools we use every single day to orchestrate workloads. We talk constantly about things like pod isolation or setting resource limits for memory and CPU. Right? But here's the thing. Kubernetes doesn't actually magically enforce these rules itself. It simply translates those concepts into actual Linux primitives. Pod isolation, that's achieved using Linux namespaces. Resource limits, those are enforced by Linux cgroups. So Kubernetes is, fundamentally, just a highly sophisticated system for managing those exact Linux kernel features at a massive distributed scale. Take namespaces, for example. A namespace is just a core Linux kernel feature that tricks a process into thinking it has its entirely own isolated operating system. It gets its own process IDs, its own network interfaces, its own mount points. So when we're talking about Docker or containerized workloads or securing an enterprise environment, what we're really talking about is configuring Linux namespaces. Containers aren't some separate, mystical cloud-only invention. They are deeply, inherently built on Linux foundations. Okay, Section 4, SRE and DevSecOps reality. Let's talk about Day 2 operations. Stepping away from just the deployment side, what do site reliability engineers actually rely on when they're deep in the trenches?
Well, look at observability and automation. Tools like Ansible and Terraform for CI/CD and infrastructure automation, or Prometheus, Grafana, and FluentDead for observability. Every single one of these is fundamentally native to Linux environments. They pull their metrics from Linux file systems, they execute shell commands, they monitor system calls. Think about it. If you're configuring a DevSecOps pipeline or trying to gain observability into a failing node, your tools are speaking Linux. If you don't speak Linux too, you're really only getting half the conversation.
And this is exactly why true cloud engineers need a very specific toolkit. The Linux command line and shell scripting, those are your basic first steps for automation. Networking, really understanding DNS and routing, is absolutely non-negotiable for system performance. And crucially, user management and security hardening. Because robust DevSecOps operations, they always start with secure patched configurations right there at the kernel level. Next up, Section 5, Linux networking and scalability.
So how do we actually apply this in the real world? When there's a massive performance drop and you're pulling your hair out at 2 a.m., an experienced architect follows a very specific top-down flow. Step 1, check the application layer logs. If they're vague or unhelpful, Step 2, inspect the container runtimes. Step 3, analyze the Kubernetes network overlay, are services routing correctly? But honestly, quite often, in the most complex scenarios, you have to go straight to Step 4, diving into the Linux kernel metrics. True root cause analysis, whether you're dealing with dropped packets, saturated network interfaces, or sneaky memory leaks, it almost inevitably ends right there at the kernel, because that is where the ultimate truth of your system's performance actually lies.
Finally, Section 6, Mastering the Foundation. There are really 4 main pillars, 4 key reasons why Linux continues to drive agility and scalability across the entire enterprise space. First, it is the universal foundation for almost all cloud infrastructure and Kubernetes nodes. Second, its open source flexibility allows it to be incredibly customized for highly specific, lightweight workloads. Third, its strong security models and super active community give you the continuous updates you need for enterprise safety. And fourth, it offers proven performance. It is battle-tested to efficiently handle literally the most demanding workloads on the planet.
So this is the overarching design philosophy I really want you to take away from this explainer, especially for any junior engineers out there listening. Cloud tools change. Kubernetes might eventually be replaced by something else down the line. The AWS dashboard is definitely going to be redesigned. Terraform might evolve. But Linux stays. Deep, fundamental knowledge of the Linux operating system actually future-proofs your engineering career because it is the bedrock that all of these evolving abstractions are built upon.
There's a quote from the source material that just hits the nail on the head and beautifully summarizes everything we've talked about today. The deeper your understanding of Linux, the stronger your cloud architectures and operational decisions. When you truly understand the kernel, you don't just guess when a system fails. You don't just randomly restart pods hoping the problem magically goes away. You make precise, informed architectural decisions that actually scale securely. So I'll leave you with this final, somewhat provocative thought to mull over. You might know your way around the cloud dashboard. You might even be able to deploy a cluster in your sleep. But when the dashboards go red and the abstractions fail, do you know its kernel? You got to dig into the foundation. Mastering Linux isn't just a prerequisite, it really is your ultimate superpower in cloud-native engineering. Thanks so much for joining me on this explainer today, and I highly encourage you to go open up a terminal and start exploring for yourself. See you next time.